So welcome to Quantum Field Theory, everyone. My name is Tobias Osborne. This course is the first course that you do after your basic undergraduate training in quantum mechanics and statistical physics. This is, in some sense, the first piece of real physics you're going to meet in your whole physics degree, theoretical physics, that is. So before we get onto the actual content of the course, I'll start by telling you the important stuff. So the important stuff is obviously got nothing to do with the material. This course is worth 5 credit points. And of course, the assessment is the thing that you'll be most interested in. So the Studienleistung for the course is to achieve more than 40% on the marked assignments. How many assignments will there be? There will be 5 assignments that are worth marks due throughout this course. Once you've achieved 40% on these marked assignments in total, then you will have got enough credit to be awarded the Studienleistung for the course. If, however, you're interested in the Prüfungsleistung, which I guess many of you are, then that is an oral exam. Please email me for an appointment towards the end of the course. So the assignments themselves are due approximately every 2 weeks, depending on Brückentage and holidays and all that sort of stuff, and other factors. These will be due approximately every 2 weeks. I will upload them to StudIP. They will come onto StudIP a week before they are due. So that's, I think, everything we need to worry about the assessment. Now, how does the course run? So we're going to have 3 plus 1 . We will have 3 lectures, one after the other, and then every 2 weeks an exercise class, usually on a Friday. Usually. Again, this may change depending on factors beyond our control. That's, I think, it for the assessment and organization. Are there any questions, any burning questions about how we're running the course?
Will you hold the exercise class or no?
There will be a tutor who will take the exercise class. That's Dennis Stiegemann. You'll see his name in StudIP. And you'll be able to contact him through StudIP. Good. Then I guess we can get now to the actual course itself. sources and textbooks. So quantum field theory is one of the most fascinating theories in theoretical physics because it is not yet mature. Quantum field theory has not yet reached a stable, agreed formulation such that everyone acknowledges this is the only way you should teach it. I mean, if you think about calculus, if you pick up a textbook on calculus, you may pick it up from 100 years ago, or you may pick up one today, published today, and they're more or less the same. The calculus textbooks all agree in how they start, more or less, and you proceed through the same topics in the same order. So calculus is a mature theory. Quantum field theory, on the other hand, is not mature in any way. It's a very exciting theory. We don't yet know what quantum field theory is, which makes it kind of difficult to teach if we don't know what it is. And that's also leads to a huge problem when I try and give you textbooks for the course, because just about every textbook you pick up on quantum field theory will do things differently. And so you can, there's a very great amount of choice in how to teach this course. Now, I'm not going to use as the primary source a textbook at all. The primary source will be some lecture notes written by David Tong, University of Cambridge. If you Google David Tong QFT, you will find these lecture notes. There's no need for me to put a link here. They are free, downloadable in PDF format. So this is the primary source for our course. These lecture notes were based in turn on some older lecture notes of Nick Manton, a well-known quantum field theorist, and another source, namely the course of Sidney Coleman at Harvard University. Sidney is now unfortunately passed on. However, his lecture notes are available in various forms, and also videos of his lectures are also available for you to download for free. Well, download not quite so easily, but you can certainly stream them from the Harvard website. So these will actually form the basis for this course, these notes. I will not follow them exactly. As you'll see, I will make very many changes throughout, but the basic structure will be due to these two, will follow these two sources. And then I will write down 4 textbooks, which I like for various different reasons. And then between those sources, you should have enough to base your studies on. So, well, which one shall I start with? Let me start with this one. There's a book by Mandel and Shaw. It's a bit old-fashioned now. This is the book that I first learnt it from. That doesn't make it the best book. It just makes it the book that I learnt it from. So I'm familiar with the contents of this book. So you will see that there's some similarity to this book. There's another book which is completely different in every possible way to Mandel and Shaw. That's due to Weinberg. He has 3 volumes on quantum field theory. Well, as you get more experience with the subject, I grow to appreciate this textbook more and more. But when I tried to learn myself from this material, I found it extremely difficult. So this textbook is really not for beginners, but it's a very beautiful presentation of the subject matter. It's just, yeah, it's not something you want to start with. And then we will have, it's hard not to talk about quantum field theory and not mention this textbook. Peskin and Schroeder is probably the most used one at the moment. I don't find it to be the best. I prefer these sources up here in terms of sheer insight, this source here in terms of the beauty of the presentation. Peskin and Schroeder is not in this, doesn't share the features that I like of quantum field theories. But chapters 2 and 4, 2 to 4 are usually correspond most closely to this course. And finally, there's a very wonderful textbook by Tony Z, on quantum field theory. It's very intuitive. If you like mathematical rigor, you will hate this book. But I think it's one of the quickest ways to really understand what's going on. It's a fantastic textbook. I like it very much. If you like rigor, then I guess this is the most rigorous. Before we get to mathematical quantum field theory, which we will not touch in this course, because, as I said, there's not yet a mature formulation for quantum field theory. So these are the sources. There's really far too much to cover when you're studying for the subject. If you want to study this subject by yourself without attending the lectures, or after you attend the lectures and you want additional material, David Tong's lecture notes are probably the best source for you to look at. That's the source material. Let's get to the outline of the course. What are we going to do in this course? Well, I'm going to give you some introductory material today. I won't put that on the outline. The first topic we're going to cover in quantum field theory isn't quantum field theory at all. We're instead going to study a purely classical theory of physics called classical field theory. And you've met classical field theory before in Maxwell's equations, in fluid mechanics, and in the theory of heat. I assume you've met in various shapes and forms classical field theory, but we will cover it in some detail before we move on to the quantum field theory. And we will then spend a long time with the simplest of the quantum fields, quantum scalar field. So we'll spend, I guess, the most part of the course on that, because everything, all our intuition in this course at least, will be built on this one example here. And then that's not enough to describe what we see around us. This only describes the bosonic part of nature. We have to talk about fermions, and hence we will move on to the quantum Dirac field. Also known as the spinor field. After we've talked about scalar fields and Dirac fields, we'll have enough to really start building fields which interact with each other. This is where quantum field theory gets really interesting. So we'll move on to interacting fields. It's all very well to build interacting field theories. Can you solve them? The answer is no, you can't solve anything that's interesting. Exactly. Instead, you have to approximate them, and we'll do so via perturbation theory. That's the next major topic in this course. And just a teeny bit on this topic of renormalization. That's the course. This is all we'll be able to cover. And even still, we will need to skip many things to cover this much. So let's start. I think we can. I've covered all the basic stuff we need to cover before we get into it. So let's start with some notations and conventions. We're going to work in units such that h bar equals c equals 1. It's surprisingly interesting to make different choices of units. You've probably done this at some point in your undergraduate education, but it's likely that you haven't spent a great deal of thought on choices of units. I recommend videos of Arkani Hamed, who speaks a little, has some videos on choices of units, natural units. For some reason I can't spell today. And what does this unit choice mean? If we make this choice of units, then units of length equal units of time can be exchanged with units of energy to the -1. So that's why we won't be writing down H bars or C's in this course. So let's get to the big question. I'll answer this one first up. So why do we want to learn, why is there even quantum field theory? That's the big question that I'll start with. And I'm going to draw you a diagram to explain why we have this theory called quantum field theory. I want you to think about your own answer to this question while I'm erasing the board. Why quantum field theory? Why are you here? I mean, maybe you're here because you need to do quantum field theory to get your degree, but some of you, I suspect, maybe more than half of you, might be interested in what quantum field theory is. Well, there's several stock answers that people give to this question. The one I'm going to give is a little different. It starts with this, a theory of everything. I think it's safe to say that we do not yet have a theory of everything. That would be a physical theory that describes all degrees of freedom in the universe, observable or unobservable. We don't yet have one of those, but we want one. That's what we really want. Right? Some people think that it's string theory, and indeed I believe that's still currently the best candidate we have, since we don't have much else. Whatever this theory of everything is, people usually agree. This is not even this. Following statement is not yet certain. People usually agree that it's got something to do with quantum mechanics, and it's got something to do with gravity. So a theory of everything is probably a quantum gravitational theory of everything. Probably. There's various we could spend several lectures just describing the thought experiments you can do to convince yourself that the theory of everything has something to do with quantum mechanics and something to do with gravity. I'll briefly sketch one argument to do with the fact that if you want to measure something with certainty in quantum mechanics, you'll have to invest so much energy that the theory of gravity will have something to say about your experiment. So as you know, in quantum mechanics is a statistical theory. It doesn't give definite answers. It just tells you relative probabilities for the outcomes of experiments. So it tells you the probability that your detector will click. If you want to estimate a physical quantity to an arbitrarily arbitrarily accurate level, so you have some expectation value, I don't know, suppose you care about the energy of a system like this. you have to repeat your experiment. Do it many, many times. Repeat it, repeat it, repeat it, repeat it, repeat it. So that you get better and better statistics. But just think about what that means. If you want to estimate this expectation value to a higher and higher degree of accuracy, you have to repeat and repeat your experiment. You have to refine your experiment. You have to have, you run into physical limits very quickly. So it gets to the point where you start to need to store this information somewhere, like, I don't know, in a computer. And you make more and more experiments, right? There's no limitation in the theory of quantum mechanics on how many times you can do an experiment. But if you start recording the results so that you can estimate this quantity, you're going to need to store the information somewhere. So you start storing it in the memory of your computer, then you run out of that, then your hard drive space, then you run out of that, and then you store it in, I don't know, high bandwidth memory stacked things, and then you run out of that. Eventually, you run out of space to write down all this information, and the more you write in, you run into other physical limits. You get to the point where you need to encode so much information in a volume of space that you will inexorably create a black hole. So this is a rather fanciful argument, but it's actually not so far from the kind of arguments that we make to convince ourselves that quantum mechanics and relativity and gravity have to be merged somehow in order to describe a theory of everything. And just the simple thought experiment of dealing with measuring an observable to an arbitrary level of accuracy, a single observable, should start to make you think. Now, we just don't know, right? We're not able to test the degrees of freedom of the universe that are relevant for our theory of everything. Unfortunately, we've been put here on this planet having access only to lower energies and larger scales. So we cannot directly test and interact with the fundamental degrees of freedoms of the universe. We can only perceive the universe by very bad experiments. Actually, we'll never ever get to the kinds of accuracies that we need to estimate this quantity here to an arbitrary level of accuracy. We're only going to be able to do relatively bad experiments. The Large Hadron Collider, for example, right? You know, we have access to degrees of freedom up to a certain energy, and then we run out of money. And at that level, in this limit of large scale and lower energy, we can access regimes where relativity is important and quantum mechanics is important. And so it's in this sense that you should think about relativistic quantum field theory. It's the theory that arises as an effective theory. It's an effective theory. We'll hear a lot about this word effective in this course. Relativistic quantum field theory is an effective theory for this thing that we want to understand. This effective theory only describes the degrees of freedom that we can access in the laboratory on Earth, or perhaps indirectly by observing astronomical events. And at this level, we are unable to distinguish between the universe being described via continuous nice quantum fields and whatever the building blocks of quantum gravity theories are. So relativistic quantum field theory is our first effective field theory of the universe. It's the one that seems to work best. Describes every experiment we've made up to this point. There are some problems with relativistic quantum field theory as a description of nature. It's not a very attractive one. People don't like what it looks like, but this is our first effective theory of what the universe is, how it's described. If you go to even lower energies and larger scales, then there's an effective theory to relativistic quantum field theory. I want to put this in this picture here. It's important. And that's called non-relativistic quantum field theory. Non-relativistic quantum field theory is quite an interesting topic. It's very useful when you describe condensed matter systems, systems that aren't a moving relativistic regime, where nonetheless quantum effects are important. And you've probably, in fact, we met some aspects of non-relativistic quantum field theory last semester in the advanced quantum theory course. By the way, I will often make reference to videos that I've made of previous courses. So my previous course, Advanced Quantum Theory, you can find that on my channel. And you just Google my name in YouTube, and you'll see that I've made a playlist for that course, and I've also made a playlist for the course before that, the theory of decoherence. So it'll be very convenient to refer to those videos in this course. So that's where you find them. Now, both of these theories I mean, it's very hard to interact with either relativistic quantum field theory, you need massive energies, or non-relativistic quantum field theory, you need like extremely cold temperatures. So this word here is decoherence. And what happens is that we're unfortunately not good enough to do experiments that can really do a good job of probing these theories. We can only access these theories usually through the lens of decoherence, which means noise. Our experiments are never perfect. And then it turns out that when there's enough noise present, that there's an even better approximation that describes all the physics we can encounter in an experiment. That's called classical field theory. So that's why classical field theory was discovered first. It's because 100 or so years ago, the experiments we could do were not good enough to perceive the difference between classical field theory and one of these quantum field theories here. The experiments we could do were not, they had too much noise present in them, and we could not reject the hypothesis that classical field theory was a good description of nature. It's here where we begin, and I want you to think, I'm going to emphasize this point throughout this course, there's a very misleading terminology that people use all the time. It's called quantization. And I myself will, of course, use this word, I'm afraid. But it's a very bad word because it suggests the wrong thing. So what we're trying to do in physics is not take a nice classical field theory and somehow use it as a building block of a quantum field theory. In physics, what we're doing is we're trying to reveal that which was there all the time. So the universe did not become quantum in 1927. It's always been quantum. The reason we don't perceive the quantum nature of the universe so easily is because of this thing, right? Decoherence here. When we're quantizing, when we use this expression quantize, what we're trying to do is guess. Quantize is another word for guess. We're trying to guess a quantum theory, a relativistic quantum field theory, or even better yet, a theory of everything, such that when you take its low energy, large scale, high decoherence limit, you end up with some classical field theory, which we already know is a good effective model for what we can see. So physics is all about doing this. It's about going backwards. Undoing these approximations, trying to guess to find out what's inside the box that's nature. Unfortunately, we are not there yet. We're stuck kind of here. I don't know how to estimate how far we are towards a theory of everything. We're kind of just past relativistic quantum field theory in going backwards along these approximations here. But we certainly don't know. So what we're going to do in this course is to describe as much as we can of the process of going along this red line here. And the most we can tell you in this course is about this theory called relativistic quantum field theory, which arises by undoing this limit here to some extent. Now, you've probably heard that relativistic quantum mechanics is hard. You know, in the popular press, much is made of how difficult the relativistic quantum field theory is. And to a certain extent, that's absolutely true. It is hard. And today, in the remaining, let's say, hour and a bit, no, I guess less than an hour, I want to tell you exactly why relativistic quantum mechanics is hard. And then, for the rest of the course, we'll start attempting to build one. So what is relativistic quantum mechanics? So I've told you why we should be interested in this theory. It's our best guess yet at what is governing the degrees of freedom of the universe. Let's get down to the what it is. What is relativistic quantum mechanics or quantum field theory? Well, I have to give you a definition, right? And here's the question, though. What does it mean to say that a quantum theory is relativistic? I'm going to give you one answer. This is already an interesting question because it admits more than one answer. But I'll give you one answer. I think this is a more traditional answer that I'm going to give you. There are more funky answers that you can give. That's one answer. The theory is symmetric under the Poincare group. Now, I'm not going to assume that you completely remember what the Poincare group is. And I'm not going to assume that you remember what symmetric under means. So we'll spend the rest of today identifying the words in this answer. And then I'll tell you why it's extremely hard to do that. Now, when you hear the word symmetric under while I'm erasing the board, I want you to think about rotations. Think about quantum theories that you know that are invariant under good old three-dimensional rotations. And think about the things that you needed to do to talk about this quantum theory invariant under rotations. I'll give you an example the most important example of a quantum system ever, that's the hydrogen atom. It's the most important quantum system there is. It's a theory invariant or symmetric under rotations. Think about all the language you needed to describe the hydrogen atom. We're going to need to build an analogous language to deal with not rotations, but more advanced rotations called Lorentz transformations. So let's recall, what is this thing, the Poincaré group? So we're going to use 4-vector notation to discuss events in space-time. So this is the 4-vector x0 through to x3. The first coordinate is the temporal coordinate. This is a coordinate system in some inertial reference frame. So if you refer to the same event in another reference frame, then the coordinates of your event in your new reference frame are related to those of the original by a transformation. That's just what we're going to get to in a second. And the way these two coordinate systems are related, the ones in the two different reference frames, is via this invariant interval here. I'm going to define this eta mu nu in a second, don't worry. So eta mu nu is a 4x4 matrix, or 2 tensor, and we're going to use this convention in our course. So it's negative signature, and we make the temporal coordinate the one with the positive sign, and we use minus signs on the rest. There are reasonable reasons to think that this is a bad choice, but it doesn't matter for our course. And we're going to use this summation convention. When you see the same index twice, it means sum over that index. The index runs from 0 to 3. So how are these two coordinate systems related to each other? That's the question. You already know the answer, of course. How is the coordinates in reference frame 2 related to those in reference frame 1? That means understanding what this Jacobian here is. And the answer is, of course, they're related by these things called Poincare transformations. So any transformation between two coordinate systems that satisfies this equation here has to be a linear transformation. Can't be an arbitrary nonlinear transformation. And in fact, we could say a little more. We could say what it looks like. It's not just any linear transformation, but it's one that looks like this. It's comprised of some kind of rotation-like thing. It's a 4x4 matrix, plus some kind of shift. So A mean U is very important. People tend to not discuss A mean U. It's like trivial, right? In special relativity. Just a shift, that's pretty trivial. You just move, right? But actually, there's a lot of physics in relativistic quantum field theory in this bit here. So we're going to keep that there throughout the course. There's really a lot of physics in there. And this thing here is what you know as a Lorentz transformation. So it's a 4x4 matrix, and it's not just any 4x4 matrix, but it has to satisfy a certain quadratic equation that's it's just directly implied by star. Has to obey that equation there. So any 4x4 matrix that you can find, that when you multiply it, or in matrix form, I'll write this in matrix form. So if you find a 4x4 matrix that when you multiply it in Mathematica and you get back eta, that's a valid Lorentz transformation. And I want you to start thinking about some simple examples, like think about the identity matrix. Just check, does it work? What about a rotation matrix? Does that work? What about the matrix eta itself? They all satisfy that equation. So they're all valid transformations. Eta is kind of interesting. It refers to spatial inversion. You multiply x, y, and z by -1, but you leave time alone. I'm not going to say so much about what the solution to this equation looks like. You've done special relativity. You can look up the answer, boosts and rotations and inversions. Now, you've probably heard me say this towards the beginning of the lecture, and you've probably heard it said that these transformations form a thing called a group. You've probably heard of mathematical groups. not the Facebook kind, but the kind which involves matrices or abstract elements. What does it mean to form a group? Well, I'm going to let you Google this, but I'll say it in words. A group is a set. So it's a bunch of things. It has a special thing called the identity. Which is the transformation. Wait, before I get to that. I'm going to write transformations of this form as pairs of a Lorentz transformation and a shift, just like this. So for these transformations to form a group, there has to be at least a thing called the identity. That means the do-nothing transformation. And that is this transformation here. The do-nothing Poincare transformation is I don't shift and I don't rotate in any way, shape, or form. I do nothing. Another property that a set needs to satisfy to be called a mathematical group is that you can take product. I'm going to in a moment describe the product for this group here. Let's call this group P4 for the moment. So the set of all Poincare transformations, if it's to be called a group, it needs to have an identity, which means do nothing. And to be an identity, I should have done this in the opposite order, but to be an identity, when you multiply anything by the identity, it also better be the original item again. So to talk about that, we need a product operation. And the product just means there's some way of putting together two items in this set and get another item in the set. So the product of two Poincare transformations had better be a Poincare transformation. And finally, the existence of an inverse. I won't write it like that, I'll just write it like primes. So for all Poincare transformations, there exists this element lambda prime A prime such that okay, so these are the axioms for a set to be a group. I've got to tell you what all this data is for this set of Poincare transformations that we write like this. So I've already told you what the identity is, but I haven't told you what the product operation is. What does it mean, like multiply two Poincare transformations? And here physics should be your guide. Multiply should mean do one then the next. So it better be the case that if I do one Lorentz Poincare transformation and then I do another, that's the same as doing a Poincare transformation, but possibly a different one. So if we do one Poincare transformation, and then we do another. So we go to one reference frame, and then relative to that reference frame, we go to another reference frame. Then that's just the same as going to another reference frame, right? So it better be the same as some kind of Poincare transformation. And indeed it is. The total effect is the same as this Poincare transformation. Multiply these two matrices here, multiply lambda bar times A, and then add A bar. And that I'm not going to prove. That's an exercise for you. You do not need to hand it to me, but it is very important to do this exercise. Because if you cannot do it, then you will start to be getting lost in this course. So this is all I want to say on the Poincare group. You can check that, oh, I didn't actually write out the definition of this product operation. Here it is. You can check that that indeed is a product operation. You can check that this item here does act as the identity. Come on, let's just do it now, right? Let lambda bar be the identity, let A bar be 0. Is it the case that I0 times lambda A is lambda A? Well, identity times lambda is lambda. A bar is, wait on, I got confused. A bar is 0, and lambda bar is the identity, so that's A. So good, good, at least that works. You have to convince yourself that there exists an inverse. So for every lambda comma A, there exists a lambda bar and A bar such that when you multiply them, you get identity comma 0. Slightly non-trivial. It's not so bad. So that's all an exercise for you, to check that pairs of matrices lambda and 4 vectors A, according to this product rule, form a mathematical group called the Poincare group. So far, that's just classical physics. There's not any quantum yet. But I want to get to to answering the question, what does it mean to have a relativistic quantum theory? Well, so we've done the relativistic. Well, we've got to now answer the question, what does it mean for a quantum theory to be symmetric? And actually, we know the answer. We saw that in the last lecture of the Advanced Quantum Theory course. It's lecture 18. You can check it out in the playlist on Advanced Quantum Theory. Something is a symmetry of quantum mechanics if it's either a unitary or an anti-unitary operator. Kind of an amazing statement. It's really the most fundamental statement underlying this course. You want to build something, you want to build a quantum theory symmetric under something, then make sure that something is represented by a unitary. So the idea of building relativistic quantum mechanics is actually pretty simple. For every Poincare transformation, we need to find a unitary operator which somehow does the Poincare transformation. And we've done this, we solved this problem for another symmetry transformation that we should be familiar with. So if you think about rotations, then we actually know how to build unitary operators that do rotations. That's what the theory of angular momentum is all about. And we're going to mirror the theory of angular momentum for this slightly bigger looking group of Lorentz transformations. So angular momentum is the theory of how to do rotations quantum mechanically. A rotation is a 3x3 matrix. Like, we've got 4x4 matrices. How hard can this be? It turns out to be astonishingly harder. Right. We're going to build our relativistic quantum theory right here and now. What do we need? Well, let's look down our list of axioms for quantum mechanics. To every quantum mechanical system, we assign a Hilbert space, right? Describing the space of states the system can enter. So we better have a separable Hilbert space handy in order to do quantum mechanics. Separable is technical requirement. It's my standing open question that I've asked many people. Do we need this technical requirement to build a reasonable theory of physics? I don't know the answer, but it's a very convenient technical requirement, but you can just think Hilbert space. Now, this is not yet relativistic, this quantum theory. It becomes a relativistic quantum theory when for every Poincare transformation, lambda comma a, we can find a unitary transformation that somehow does that transformation. We have a relativistic quantum theory when to every Poincare transformation, we have our desired Poincare transformation, we know which one it is, we can find a unitary operator, u lambda a from h to h. Now if we stopped right there, then that's super duper simple, right? You just choose your favorite unitary transformation for all lambda comma a. But you haven't honestly done a Poincare transformation on your quantum mechanical system, have you? If on Thursdays you choose the identity, and on Wednesdays you choose a rotation, that's not doing a Poincare transformation. So we need to give it some conditions before we can happily say that this is doing a Poincare transformation. And so what we need is that when we do, you just look at the axioms for what it is to be a Poincare transformation, and it turns out that in the least, right, you'd want that when you do the identity transformation, you better get the identity. So let's write that down, right? If you're doing the identity Poincare transformation, this had better be proportional to the identity. If I don't do anything, then the most that I'm allowed to do is something unobservable, which is in fact multiplied by a phase. So you can't just choose any old Poincare unitary operator. It has to do at least that. Now that still isn't doing a Poincare transformation. It does it when it does the right thing under products. And then it turns out that's what it means to do quantumly a Poincare transformation. We've done a quantum Poincare transformation when we take one quantum Poincare transformation, do another, and we cannot physically distinguish that from having done this product here. That's what it means. And what does it mean, physically indistinguishable? Well, it means that up to a phase that depends on lambda comma a and lambda bar comma a bar, that this is the same as lambda bar lambda, lambda bar a plus a bar. So this is what it means, physically indistinguishable, right? This is just a phase. So if you think you've found a way to do a Poincare transformation on a quantum system, then I claim you'll at least have found unitary transformations U that obey properties I and II. This looks innocuous enough, but be warned, right? There's an infinite number of equations here. So for all lambda, there's an infinite number of lambdas, right? Just choose different rotations, for example. You need that the unitary transformation you're assigning to this transformation obeys this property for all lambda comma a and lambda bar comma a bar. It's actually a lot of conditions that we've written down here. We have a fancy name for things that obey these two conditions. They're called projective unitary representations. So if you want to look up the mathematically precise literature, the right language to use is that of projective unitary representations. Now, it doesn't really look that hard to do this. In fact, for a long time, I thought this was easy. Right? I refused to be convinced this was difficult. And the first gotcha, right, the one that the first representation you should think of. You know, if you want to build one, then start thinking of one. You must have your favorite example in mind. You know, one of them is just assign the identity to every Poincare transformation. That's a legitimate projective representation, except it doesn't really do anything, does it? So that's not, that's still trivial. But if you want to build a non-trivial one, then you might think, well, maybe all I need is a 4-level quantum system. I mean, after all, there's a perfectly good representation of Lorentz transformations, which is just let U be lambda. Just think about that for a moment while I... You know, if you throw away translations, just throw them away for the minute. Suppose we live in a universe with where we're all stuck on the same point. Then you might be a long way toward your goal of building representations if you just choose for U the 4x4 matrix lambda. Does anyone see what's wrong with that? choosing for U the 4 by 4 matrix lambda. It certainly obeys these two conditions. Yep. It might be non-unitary. Exactly, it almost always is. So that's the problem. You run into not these two conditions, but you run into the constraint that it has to be unitary. So it turns out that satisfying unitarity and 1 and 2 is really hard. And in fact, that's the sort of the first sign that things are super difficult in quantum field theory. So let me quote you a theorem. This is still fairly rigorous. There are no non-trivial Okay, this is bad news. There are no non-trivial finite dimensional representations that are unitary of the Poincare group. Now this is in super stark contrast to rotations. There's loads of finite dimensional representations of the rotation group. And the unitary representations are given by, let's call it xjx, iy. So if you sort of remember angular momentum theory, you remember that you constructed these jx, y, z's, and they were finite dimensional matrices. They obeyed this commutation relations. And then once you have these three matrices here, you remember you constructed finite dimensional j's, you did 2 by 2 ones, you did 3 by 3 ones, possibly you did even larger ones. And it turns out that this unitary here is a nice projective unitary finite dimensional representation of rotations. So that's for those of you who are comfortable with angular momentum. So the theory of angular momentum is really the theory of the representations of SO3. And if you look at the condition to be a Lorentz transformation, it's not that far different from being an SO3, a rotation. So remember, a rotation is just is a 3 by 3 matrix that satisfies that. I'll use a different notation actually. So why did it get hard? Well, the answer is this is if you have some mathematical training, the answer is that this is a compact group and the Poincare transformations form a non-compact group. So that's the mathematical reason. The physical reason is also kind of interesting. So we'll see that throughout this course. Okay, let's talk about subgroups before I mention some other bad news. Oh yeah, I didn't explore the consequences of our bad news. So if there's no non-trivial finite dimensional unitary representations, that leaves us only with infinite dimensional representations. And that's sort of the first reason why relativistic quantum theory is hard. We can't build things from finite dimensional pieces. And now I'm going to tell you even more bad news, and it's got to do with subgroups. So let's consider the set of all Lorentz transformations that have this form, of all Poincaré transformations, sorry, not Lorentz, of all Poincaré transformations that look like no boost, no rotation, just a shift in time. So this is clearly a subset of P4. I mean, every one of these transformations here is a Poincaré transformation. It's even a subgroup, meaning if you take the product of two of them, you get another one in here. And it's called the time translation subgroup. It's just the set of all transformations that move us forward in time. Time translation subgroup of all Poincaré transformations. So it turns out that just waiting 1 second is also a Lorentz transformation. Waiting 10 seconds, waiting till the end of this lecture in 15 minutes is also a Poincaré transformation. Sometimes we wish we could do those transformations to make time pass faster. And maybe if you had a quantum computer for a brain, you could simulate time faster and then watch Game of Thrones in the meantime or something. Now it turns out that getting a unitary symmetry transformation for every element of this group here, let's call it, I don't know, script VT for time. If we just focus on the lesser task of finding a unitary operator that does just that Poincaré transformation, then we're already doing something pretty non-trivial, because it turns out we're doing quantum mechanics. So let's suppose we found ourselves somehow, through some divine insight, a unitary representation of the Poincaré group. We've got a quantum system that's relativistic. Then this set of unitary transformations here, which I'm calling V, then these transformations V is a one-parameter family of unitaries such that we have this property turns out we have another name for that. They're called propagators. We've met these before. They're solutions to Schrödinger's equation. Well, going to abuse notation slightly. So having a representation of the Poincare group is already solving the Schrödinger equation. Because to represent the Poincare group, we at least need to be able to wait. We need to wait for 10 seconds, for a minute, for 15 minutes. And the action of waiting in quantum mechanics is letting Schrödinger's equation evolve. Because Schrödinger's equation tells us how time passes in quantum mechanics. So having a unitary representation of the Poincare group is strictly stronger than solving Schrödinger's equation. But, you know, we're demanding. In physics, we're very demanding. We're not happy if H is self-adjoint. We want that it has no eigenvalues that go off to minus infinity. Because if your Hamiltonian has arbitrarily negative eigenvalues, then it's unstable. The system can just emit particles and go to a lower and lower and lower energy configuration forevermore. And that's bad, because we seem to be pretty stable here. So we want to make sure that our theories of nature are stable. So we're going to require that our projective unitary representation of the Poincare group is so-called positive energy. And this already makes life so much more difficult. That the spectrum, you know, the eigenvalues of H is contained in the positive real numbers. We're not allowed to have too many negative eigenvalues. That's the content of that statement there. You can always get rid of a finite number of negative eigenvalues just by adding the identity. But you can't get rid of an infinite number of negative eigenvalues by adding the identity. Well, negative eigenvalues that go off to minus infinity. So we're going to demand that these representations are so-called positive energy, and that means because we don't want things to be unstable. Because if things aren't positive energy, then it's easy for our quantum systems to just decay into masses and masses of particles by interacting with another system. So that's another constraint that makes our life more difficult. Now here's some good news after all this bad news. So this makes our life harder. But the good news is that actually all the representations of the Poincare group have been classified. Finally, some good news. Not only can we find unitary transformations which obey all the constraints that I've written down, we can even classify them. We know every one of them. In the case of single particle theories. So all such single particle unitary representations, that's where our Hilbert space refers to just a single solitary particle in the universe, no friends, no one else. All those transformations have been classified. We know how to write them. They were classified by Wigner very long ago in a really triumphant, fantastic piece of work. And they're labeled by two numbers, the mass of the particle, which is invariant under Lorentz transformations and Poincare transformations, and the helicity or spin S. And in fact, you might think, okay, well, we could just get and study these unitary representations. That's a sort of perfectly valid thing to do in relativistic quantum theory. However, we're going to end with some more bad news. I'm not going to do that. Although this is a lovely piece of mathematics and would occupy us for approximately 18 lectures to do everything right, do it carefully, there's no point. Because nature chooses not to be a theory of single particles. Nature chooses to be a theory of many particles. Otherwise the universe would be pretty boring, right? It would be just one particle. There would be no you, there would be no me. There is many particles in the universe. And the minute you have more than one particle, it gets complicated. Because you have to say, how does that space of two particles decompose into copies of this single particle space? And the answer is with great difficulty. Okay, that might be a doable task. But things get much worse when you want those particles to interact. And we know that particles interact, right? We can't hide it. We can't hide the fact that when we shine light at an electron, that the photons interact with the electrons. And even then we might be saved. If the interactions were if we didn't care that the interactions were local or non-local, then we actually probably get away with it and be able to understand relativistic quantum mechanics. But we have this other constraint that we like very much in physics, and that's to do with locality. And it turns out that the minute you impose that constraint, you force yourself to allow your theory to have not a definite number of particles. So there's multiple thought experiments you can do to convince yourself that the number of particles in a relativistic quantum theory that's local cannot be fixed. So I'll invite you to think of the following example. Imagine you have a particle of your theory and you put it in a box, right? You want to make sure it's somewhere. So you have the particle in the box. Now it's between my two fingers. So it's pretty certain where it is. It's in the box somewhere. And its momentum, well, you know, it's a little bit uncertain, right? We have this uncertainty principle. So you start squishing the box. You want to make sure that that particle's really there. So then it's getting more and more certain where the particle is, but less and less certain what the momentum is. And you keep squishing it, keep squishing it, keep squishing it. The particle, because of the uncertainty relation, its energy, its momentum is all over the place, its energy distribution is all over the place. And at a certain width, those energies, the range of energies over which the particle's momenta is distributed, reaches this threshold to create more particles via interactions. And so just in the act of localizing a single particle, you allow quantum mechanics to tunnel into configurations with more than one particle. So that is why it gets difficult if you want to impose locality. And so far, I think it's true, the only way we know to impose locality is to go way more infinite than what we're doing here. So this is infinite dimensional, right? Single particle unitary representations. This is already infinite dimension. It's a separable Hilbert space, L2 of R, well, crossed by spin. So that's a nice, tame, infinite Hilbert space. But it turns out the only way we know how to build representations that that are local is we have to go like way more infinite. We have to go 2 to the power of that, so to speak. We have to second quantize. We have to talk about fields. And so it is that in our next lecture, we're going to begin by talking about fields. So that's it for today, and I thank you very much.